Every breath you take right now is a free service provided by a planet. You do not manufacture the oxygen. You do not remove your own carbon dioxide. You do not push the air around your bedroom so you do not suffocate inside a bubble of your own breath. You do not collect yesterday's urine, turn it back into drinking water, split some of that water apart, and use the oxygen to breathe tomorrow. Earth handles most of this quietly. Now remove Earth. Put a group of humans inside a metal. Structure roughly 250 miles above the planet. Make the structure travel about 17,500 miles per hour. Let it circle Earth every 90 minutes, and then tell the people inside, live here for months. The International Space Station has been continuously occupied since November 2000. It circles Earth roughly 16 times every day, meaning its residents can experience around 16 sunrises and sunsets in 24 hours. And when you first look at the ISS, the obvious thing to notice is the engineering: solar arrays, laboratories, robotic arms, docking ports, millions of parts. But the most impressive machinery may be doing something much less glamorous. It is pretending to be Earth, because outside the station, there is no breathable atmosphere, no running water, no grocery store, no sewer, no natural ventilation, and almost nothing a human body expects the environment to do automatically. So the real question is not, how do astronauts survive space? It is, how do you build a tiny artificial world where ordinary human life can happen at all? Start with air, because this becomes urgent remarkably quickly. Inside the station, astronauts live in a pressurized atmosphere, but simply putting oxygen inside a metal tube does not solve the problem. Humans are inconveniently active chemical processes. We breathe oxygen. We exhale carbon dioxide. We release moisture. We produce heat. Our bodies emit trace compounds. Equipment does too. Leave enough humans inside a sealed spacecraft, and eventually the air becomes something humans should not be breathing. So the ISS has an environmental control and life support system. NASA calls it ECLSS. Among other things, the system manages atmospheric conditions, removes contaminants and carbon dioxide, supplies oxygen, handles water, and supports waste management. Already, this is stranger than a normal house. At home, opening a window is a legitimate environmental control strategy. On the ISS, opening a window would be considered a significant procedural error. But there is another problem. Air itself behaves differently when gravity stops doing one of its invisible jobs. On Earth, warm air rises, cool air sinks. Natural convection helps move gases around us. In microgravity, that familiar buoyancy-driven circulation largely disappears. So if an astronaut breathes into poorly ventilated space, the carbon dioxide they exhale does not reliably behave the way it would in your bedroom. It can accumulate locally. NASA has studied difficult-to-detect carbon dioxide pockets around crew members, and spacecraft standards specifically require ventilation sufficient to prevent stagnant CO2 and thermal pockets. ESA describes the ISS as dependent on forced airflow because without it, exhaled carbon dioxide could collect around an astronaut's head, which produces one of my favorite facts about living in space. Fans are life support equipment, not just comfort, not just air conditioning, life support. A fan failure in your bedroom is annoying. A spacecraft where air stops circulating is a completely different conversation. This matters even when astronauts sleep. ISS crew quarters use forced ventilation, and airflow has to reach the astronaut's head while also balancing temperature and noise. NASA engineering work on the crew quarters describes a two-fan push-pull system designed to deliver fresh cabin air to the sleeping crew member. So imagine going to bed, you climb into a sleeping bag, you attach yourself so you do not drift around the cabin. There is no mattress supporting your body because your body does not need supporting. And nearby, a fan has to keep moving your breath away from your face. Space has somehow made sleeping horizontally optional and ventilation mandatory. Then, the station has to remove the carbon dioxide everyone creates. NASA's air revitalization systems circulate cabin air through hardware designed to remove trace contaminants and capture carbon dioxide. And the oxygen the crew consumes must be replaced. One major method is wonderfully direct. Take water, run electrical current through it, break the water molecules apart. Keep the oxygen. The ISS oxygen generation system uses electrolysis to separate water into oxygen and hydrogen. The oxygen goes into the cabin atmosphere. The hydrogen can be vented or used with captured carbon dioxide in a Sabatier process that produces water and methane. The water can return to the crew's resource loop. In other words, an astronaut breathes oxygen, exhales carbon dioxide. Machines capture parts of that waste. Chemistry converts some of those materials, and parts of the cycle become useful again. Earth has forests, oceans, weather, and an entire biosphere helping manage atmospheric chemistry. The ISS has racks full of plumbing, and that brings us to water. Because launching water into orbit is expensive. Also, humans insist on drinking it every day. A crew needs water for drinking, preparing food, hygiene, and other operations. But every kilogram of water sent to orbit is another kilogram a rocket has to lift. So the station tries very hard not to throw water away. NASA's water recovery system collects wastewater, including urine, cabin humidity condensate, and water associated with spacesuit systems. It processes that water through filtration and catalytic treatment, checks its quality, and returns acceptable water to storage for reuse. NASA's current ECLSS reference says the station's water recovery system recycles about 90% of its water. Think about cabin humidity. An astronaut sweats. Moisture enters the cabin air. The station captures some of that moisture, processes it, and eventually, someone can drink water containing molecules that were previously floating around the station as humidity. This is not disgusting. This is excellent engineering. The molecules are not emotionally attached to their previous employment. And yes, we have reached the urine. You knew we would. Urine is valuable in space. NASA's water recovery hardware processes urine so that water can be recovered instead of continuously replacing it with water launched from Earth. In 2023, NASA announced that an upgraded configuration involving a brine processing system had demonstrated an overall water recovery milestone of about 98% in the station's life support loop. 98%. At that point, wastewater starts sounding less like garbage and more like temporarily inconvenient drinking water. NASA has even used a memorable description of the station's closed-loop approach. Yesterday's coffee can help become tomorrow's coffee, which is both inspiring and probably not the slogan the coffee industry was waiting for. The toilet itself reveals another invisible job gravity normally performs. On Earth, you sit down. Gravity has already read the instructions. In orbit, gravity is no longer available for waste management duty, so space toilets use airflow. NASA explains that fans pull urine and feces away from the body and into the correct receptacles. Foot restraints and handholds keep the astronaut from floating away during the process. This means the toilet is partially a vacuum cleaner problem, which is probably not how most plumbing courses begin. Urine can enter the water recovery system. Solid waste is collected separately in sealed bags and canisters. Most fecal canisters are eventually loaded aboard disposable cargo spacecraft that later burn up during atmospheric re-entry. So Earth's atmosphere eventually becomes the garbage disposal. We have managed to turn re-entry heating into taking out the trash. And ordinary trash has the same logistics problem. Food packaging, wipes, used clothing, disposable materials, broken items. You cannot put them outside the station and wait for Tuesday morning collection. NASA says common ISS trash is bagged, stored temporarily, and loaded into spent resupply vehicles. Some cargo spacecraft are then deliberately sent into destructive atmospheric re-entry, where the spacecraft and its trash burn up. Other vehicles, such as Dragon, can bring selected cargo and scientific samples safely back to Earth. So even garbage is part of orbital traffic planning. A spacecraft arrives carrying useful mass. The crew unloads it. Eventually, some spacecraft become giant trash containers. Then, Earth's atmosphere finishes the job. Very efficient, slightly dramatic. Food creates a different set of problems. Again, gravity has quietly been helping you. Put bread on a table. It stays on the table. Break off a crumb. The crumb falls. In microgravity, the crumb has ambitions. It can float into equipment, into someone's eye, possibly somewhere nobody wants to find it later. NASA notes that bread produced troublesome floating crumbs in early spaceflight, while tortillas proved far better because they do not create the same crumb problem. Tortillas became standard fare aboard the ISS and are used for everything from breakfast wraps to peanut butter and jelly sandwiches. Space exploration has produced rockets, advanced robotics, orbital laboratories, and one very strong argument for tortillas. Most station food is packaged for long shelf life. Some is freeze-dried and rehydrated. Some is thermostabilized. Fresh food can arrive aboard resupply spacecraft. But without an ordinary supermarket or a large household refrigerator, the food system has to be designed around storage, nutrition, mass, packaging, and periodic deliveries from Earth. NASA says ISS crews can choose from roughly 200 standard menu items, supplemented by personal choices. And this introduces the system the ISS still cannot close. Food. Astronauts can recycle water, they can regenerate oxygen, they can scrub the atmosphere, but they are not growing enough food aboard the station to feed the crew indefinitely. Cargo vehicles still have to bring supplies from Earth. Recent ISS resupply missions continue delivering thousands of pounds of food, fuel, experiments, hardware, and other supplies, so the station is not completely independent. It is more like a house with an extremely complicated delivery address. And if you enjoy seeing the hidden systems that make human life possible where the normal rules stop working, subscribe. Because so far, we have only solved breathing, drinking, eating, and going to the bathroom. The human body itself is now preparing to become a problem. On Earth, gravity is constantly loading your body. Your legs support you. Your spine carries weight. Your muscles work whenever you stand. Bones respond to mechanical loading. Then, an astronaut reaches orbit, and suddenly, standing is unnecessary. Walking is unnecessary. Even holding your own head up becomes dramatically easier. This sounds fantastic. Your body disagrees. Without normal gravitational loading, muscles and bones can weaken. NASA's ISS crews therefore average roughly 2 hours of exercise every day to counter muscle and bone loss associated with microgravity. 2 hours every day. Imagine receiving the greatest excuse in history not to go to the gym. I am currently orbiting Earth, and NASA still says, nice try, squats. But ordinary weights do not work properly in weightlessness. Take a dumbbell into orbit. It still has mass, but it does not sit heavily in your hand the way it does on Earth. So the station recreates exercise loading mechanically. Astronauts use equipment including the Advanced Resistive Exercise Device, or ARED, which allows movements similar to squats, deadlifts, and presses. They use a treadmill while restrained to it, and they use a cycle ergometer. These are not recreational luxuries. They are countermeasures against a body adapting too successfully to space. That is an important idea. The human body is adaptable. Unfortunately, sometimes it adapts to exactly the environment you do not want it to become permanently optimized for. In microgravity, your body learns, apparently, we do not need all this muscle. NASA replies, please keep it. You will need it when we return you to a planet. Sleep creates another negotiation. The ISS circles Earth every 90 minutes, so relying on sunset as your cue for bedtime would be disastrous. You could experience roughly 16 sunrises every 24 hours. NASA therefore uses structured schedules and controlled lighting to help maintain normal circadian rhythms. Astronauts have private sleeping areas. They secure sleeping bags so they do not float around, and the sleep environment has to account for temperature, light, noise, carbon dioxide, and airflow. This creates a wonderfully strange bedroom. No bed required, no pillow required in the normal sense, no preferred side of the mattress. But your lighting schedule matters, your ventilation matters, your CO2 matters, and your sleeping bag needs to remain approximately where you left it. Even the concept of floor and ceiling starts dissolving. On Earth, architecture has a strong opinion about direction. Floors are down, lights are above. Storage tends to respect gravity. In orbit, almost any surface can become useful. Astronauts float through modules. Equipment covers walls. Objects are restrained with Velcro, straps, bags, and fixtures, so they do not simply migrate into another part of the station. And housekeeping becomes surprisingly important. ESA notes that unsecured objects are easy to lose in microgravity, making regular cleaning and organization essential for safety and efficiency. Because when something disappears in your house, you check under the sofa. When something disappears in orbit, under has become philosophically complicated. Then there is the station itself. The ISS is enormous by spacecraft standards. NASA describes its living and working volume as larger than a 6-bedroom house, with sleeping quarters, bathrooms, exercise equipment, and the cupola observation module. Its solar array wingspan is longer than an Airbus A380. But none of that space behaves like an ordinary house. A house rests on the ground. The ISS is permanently falling. That sounds alarming. It is actually orbit. The station is moving sideways so quickly that while gravity pulls it toward Earth, Earth curves away beneath it. So astronauts are not floating because gravity disappears at 250 miles altitude. They are floating because the station and everything inside it are continuously falling together around Earth. Your drink, your spoon, your body, the entire laboratory, all falling, very successfully. And the station still needs energy. Large solar arrays convert sunlight into electricity for the spacecraft. NASA lists 8 main solar array wings and tens of kilowatts of electrical generation supporting station systems and research. That electricity runs experiments, computers, pumps, lighting, communications, life support, and, critically, the systems that manufacture the environment humans require, which means the station is not simply a container with astronauts inside. It is an active machine that must keep producing normal temperature, pressure, airflow, oxygen, clean water, power, waste handling. Normal is a product. This may be the biggest reversal of the entire subject. On Earth, survival feels passive. You wake up and the atmosphere is still there. Gravity still works. The sink still contains water. Your carbon dioxide has left the bedroom. Food exists somewhere nearby. Waste can leave your home through plumbing and municipal systems you may never see. The environment and civilization do thousands of things in the background. On the ISS, the background has been removed. So engineers had to rebuild it, piece by piece. And once they rebuild it well enough, the extraordinary begins to look ordinary. Astronauts answer emails, clean equipment, exercise, prepare meals, perform experiments, talk to their families, take photographs, sleep. Someone complains about maintenance. Someone looks for an object that floated away. Someone has to repair a toilet. This is happening inside a spacecraft, traveling approximately 5 miles every second. There is something wonderfully human about that. Build one of the most technologically sophisticated objects ever. Created, put it in orbit. And eventually, somebody still has plumbing problems. But the ISS has another advantage that future deep space crews may not have. Earth is close, not physically close in the normal sense, but logistically close. Cargo vehicles can still reach the station. Mission control can support crews continuously. Replacement parts can be launched. Food can arrive. experiments can return. NASA explicitly uses the ISS as a testbed for systems needed on future missions, where resupply will become much more difficult. Mars changes the equation. You cannot casually send another cargo vehicle because someone needs a replacement filter. The farther humans travel, the more completely their tiny artificial world must recycle what it already has. Water, air, materials. Eventually, perhaps even more of its waste. The ISS is where we are learning how difficult that really is. So look at the station again. Solar panels, laboratories, modules. Robotic, farms, beautiful view of Earth. But now imagine removing the labels. What is this machine actually doing? It is holding pressure against vacuum. It is manufacturing oxygen, removing carbon dioxide, moving air because gravity will not, recovering water from urine and humidity, turning electrical power into an artificial environment, collecting waste without gravity, burning trash inside disposable spacecraft, importing food, forcing humans to exercise because their bodies are adapting to weightlessness, creating artificial days while 16 natural sunrises pass outside, and doing all of this continuously because the people inside do not get to stop needing Earth-like conditions just because Earth is 250 miles below them. That is what makes the International Space Station so oddly possible. The remarkable achievement is not simply that humans reached orbit. We learned how to do that decades ago. The remarkable achievement is that after reaching a place where almost every basic assumption of human life stops working, we built substitutes. A fan replaces convection. A machine helps replace part of the water cycle. Electrolysis helps replace atmospheric oxygen renewal. A treadmill replaces gravitational loading. A spacecraft becomes a garbage truck. Artificial lighting helps replace sunset. And a collection of pipes, pumps, filters, fans, computers, and human routines replaces a planet. Not completely, not forever, but well enough that someone can float into a small compartment, open a package of food, look through a window at Earth, and call this place home for months while moving at 17,500 miles per hour and breathing air that only exists because the machine around them keeps making Earth where there is none.